Hi, this is Manuel Garcia, and this is section 17.4, equations of motion, rotation about a fixed axis. And the objectives of today's lessons are to analyze the planar kinetics of a rigid body undergoing rotational motion only. An example of this is the pendulum of sharp impact that is shown in the figure, and it consists of a heavy arm that is usually released from a horizontal position, and it hits a specimen that is located in the bottom part, and it breaks it. And when that happens, then we analyze the type of failure. Notice that this device is only moving in the rotational form and is not translating. Let's now consider our equations of rotation about the point O. The point O is considered a fixed point about which the rigid body is rotating. Now, a rigid body can be considered like a system of particles. So if we think this like a system of particles, every of these single particles will have a differential of mass, and we should analyze uh, as a system. So that means that we can define the center of mass. So remember that the center of mass is a point representing the mean position of the matter in a rigid body. Is like the weighted average. So like the weighted average of the position, and the weight is the mass. So the higher the mass, the higher the weight. So if we sum over all the different particles that we have, so that's the integral because the system is continuous. So we have that this average is equal to the position Rg, which is the position of the center of mass, multiplied by the total mass. So this is our definition of the center of mass. So it's a point representing the mean position of the matter as we concentrate all the matter in this point, and the point is called G. Now, the best way for analyzing this type of system is to describe it with a Tn coordinate system, like a normal and tangential. So the normal forces will point from our point to the center, and it's general from a point. It doesn't have to be the center of mass, and the tangential which are perpendicular to the normal. So let's choose a particular point. So this point is our dm, which is located at a distance r. So what we have is that the sum of the forces in the normal direction is equal to this dm, to this differential of mass, multiplied by the normal acceleration. So the normal acceleration will be that, and the tangential acceleration will be that. So the normal acceleration is always given by omega squared r. Well, in this case, we don't have to have the vector because we already saying that's the direction, the normal direction. So in magnitude, it will be equal to dm multiplied by omega squared multiplied by r. And so if we integrate over the whole domain, so that means that we are adding the forces of every single of the particles in our body. So that's the integral. So we have the integral of omega squared r dm. I just swapped this dm to the left-hand side. So we have to do the integral over the rigid body. And because omega, the angular velocity, is the same for any particle in our system, so we can move it out of the integral. So this is omega squared, and inside the integral we have the integral of r dm. So that's the actual definition of the center of mass. So that means that is rg multiplied by m. And we can have it in magnitude, doesn't have to be vector because this is just the normal direction. So let me get rid of this vector because this is in magnitude. The sum of the normal forces is equal to omega squared multiplied by rg, the distance to the center of mass, and multiplied by the total mass. In a similar way, we can do for the tangential direction. So we consider every single of the particles and we add then the contribution. Notice that when we add the contribution of the forces, so we are summing over the internal and external forces, and only the external surface forces survive. So the same way, for the tangential, we have that the sum of the forces in the tangential direction, let me delete the vector because this is just magnitude, is equal to the acceleration, the tangential acceleration of the center of mass multiplied by the total mass. And the tangential acceleration is equal to r multiplied by alpha. So this is in magnitude and multiplied by the mass. So in conclusions, so the questions that we have is the sum of the forces in the normal direction is equal to omega squared multiplied by the mass multiplied by the distance to the center of mass, and the sum of the forces in the tangential direction, and these are external forces, is equal to alpha to the angular acceleration multiplied by the mass multiplied by the distance to the centroid. Let's now consider the moment about our center of rotation. So let's consider that this is our rigid body. So remember, our rigid body is composed by a system of particles of mass dm, and so every single one of these particles is located at a distance r from the point of rotation, and this particle will have therefore some normal acceleration and some tangential acceleration. So for this system of particles, so every one of these particles will have some forces. So what we previously said is that the sum of the forces of our particle is equal to the differential of mass multiplied by the acceleration, right? So that's the acceleration that it's also decomposing normal and tangential acceleration. Now, if we take the moment of the forces, so basically we need to pre-multiply by the r vector, by the position vector. So we have, and we do for every single of the forces. So we have that the sum of r cross fi should be equal to r cross the acceleration multiplied by dm. Well, dm is a scalar, so I just put it in the later position. So these are the moments for this particle, and now we have to do it for all the particles in our rigid body. So that means that we have to integrate. So we integrate, so this is the integrate of the sum of the forces, well, the position multiplied by the forces, and that should be equal to the integral of r cross the acceleration position cross the acceleration differential of mass. Okay, so when we sum all of these little moments, so a lot of the internal will cancel and only are going to survive the external moments. So let me put it in terms of the external moment. So this is the sum of the external moments around O, because R is measured from the position O. And so the survivors are the moments due to the external forces. And that should be equal to the integral of the right hand side. So the integral of the position cross product the acceleration dm. But that acceleration can actually be expressed in terms of the tangential and the normal acceleration. So this is r cross the tangential acceleration plus the normal acceleration multiplied by the differential of mass. Now let's have a look to what this cross product. So we have r cross at. So r cross at will have some value. However, when we do r cross an, the cross product of two vectors that are parallel, because an is in the same direction but in the opposite sense. So this cross product, it will be 0. So the second cross product will be 0. And therefore, this can be simplified as the integral of r cross the tangential acceleration multiplied by dm, and the integral over the whole body. So now the tangential acceleration is at the same time equal to alpha cross r. So this is equal to the integral of r cross alpha cross r dm. So now this triple cross product can be simplified. Notice that alpha cross r, alpha is in the k direction, cross product r, it will produce a vector in this direction, and r cross a vector in that direction will give again a vector in the k direction. So in the direction of alpha. So this is equal to, in magnitude, r squared multiplied by alpha vector, because it's in the direction of alpha, dm. And alpha is the angular acceleration that is constant for the whole body. So the sum of the external moments is equal to alpha multiplied by the integral of r squared dm. And so this is the moment of inertia. So in conclusion, we have that the sum of the moments of the external forces is equal to alpha multiplied by the moment of inertia with respect to O, because R is measured from O. Now, what is that moment of inertia? So how can we deal with this moment of inertia with respect to O? Because we usually have the moment of inertia with respect to G. Let's put the point G there. So assuming that this is the center of mass. So we can use the theorem of parallel axes. So the theorem of parallel axes so we have that the moment of inertia with respect to 0 to O is equal to the moment of inertia with respect to the center of mass plus the mass multiplied by the distance. So the distance is rg squared. So that's the distance in between this and that point. Let me put it in red. This is rg. So that distance is squared. So alpha multiplied by the moment of inertia with respect to O, which is the one that we have over here, is equal to alpha multiplied by the moment of inertia with respect to g plus the mass multiplied by alpha multiplied by rg squared. So we can divide this r squared as r multiplied by r. So let me put it like that. And so we have that alpha multiplied by r, alpha multiplied by r is the tangential acceleration. So we can rewrite this like alpha multiplied by the moment of inertia with respect to O is equal to alpha times the moment of inertia with respect to g plus the mass multiplied by the tangential acceleration of the center of mass multiplied by rg. So in conclusion, so if we replace this value over here, so we have that the sum of the moments with respect to O is equal to alpha multiplied by the moment of inertia with respect to g plus the mass multiplied by the acceleration of the center of mass in the tangential direction and multiplied by rg, which is the distance from the point of rotation to the center of mass. Now, what is the general procedure to analyze this problem? So we start to establish an inertial coordinate system and specify the sign of the directions, the normal and the tangential direction. We have to draw the free body diagram and account for all the external forces and couples. And then we draw the kinetic diagram and we show the resulting inertial forces and the couple. So we compute the mass moment of inertia. We write the three equations of motion and identify the unknowns and then solve the system of unknowns. If we have more than three unknowns, then we have to use some kinematic relationships to solve our system. Okay, let's have an example. So we have a rod with a mass of 20 kilograms and is rotating with respect to this point, and we have a moment that is applied to the bar. So the bar is being accelerated in this direction because we have a moment, and of course it will have an angular velocity, but the initial angular velocity is 5 radians per second. So we need to find the angular acceleration and the reactions at point O when the rod is in the horizontal position. So in the horizontal position, we need to compute both alpha and the reactions that are two reactions in these two directions. So what is the plan? How do we solve? So the mass center of the center of mass, it will move in a circle, and that will be of a radius of 1.5 from this point. So the acceleration will have some normal component and some tangential component. So in particular, so this point will be like at half the way. This is 1.5, and then so we have some tangential acceleration and some normal acceleration. So we have to set up our equations for that situation. So we start by drawing the free body diagram. Let me draw here the free body diagram and the kinetic diagram. So for our free body diagram, what we have to is disconnect from this support. So when we disconnect from this support, we end up with two reactions. So the reactions are called O in the y direction and O in the x direction. So these are the two forces that we have. We have at the support. Then in the center, so this is G, we have the weight. And do we have any other force? Yes, we have a moment that is applied here, and this moment is 60 Newton meters. Okay, so this should be equal to the kinetic diagram. So in the kinetic diagram, we consider our bar, the center of mass, and the two accelerations. So the mass times acceleration of g in the tangential direction, the normal acceleration, which is mass times the acceleration of g of the center of mass in the normal direction. And we have additionally the moment of inertia with respect to g multiplied by alpha. Okay. Now we can set up our equations. So the first equation that we have is the sum of the forces in the n direction. So in the n direction we have OX, and that should be equal to the right hand side. So this section is this part, and this is the equal, and then we have to locate the equivalent in the kinetic diagram. So we have this is equal to the mass multiplied by the acceleration of the center of mass in the normal direction. And this is equal to the mass. So what is the normal acceleration? The normal acceleration is defined as r multiplied by omega squared. And we have the values for omega, we have the values for everything, so we can replace. So the mass is 20 kilograms. So the mass is 20 kilograms multiplied by r. R is the distance from here to there. So this is r. And so that's 1.5 meters. And multiply by omega squared. So omega is 5. So multiply by 5 squared. And so when we put this in the calculator, this should be 750 newtons. Now we have our sum of forces in the tangential direction. Let me change this color. So we have in the y direction, we have this, we have that, and we have that. Okay. In the forces side, so we have OY minus the weight equal. So in the right hand side, we have the mass multiplied by the acceleration in the tangential direction. And so this is the mass multiplied by the tangential acceleration is alpha multiplied by rg in magnitude. So we can replace numerically. So we have OY, which is still unknown, minus the weight. We know the mass, which is 20, multiplied by the gravity, 9.81, equal to the mass to the mass here, which is 20, multiplied by alpha, which is unknown, and multiplied by Rg, which is 1.5. So from this equation, so from the first one, we can solve directly for Ox. So X is solved. But in this case, we have two unknowns. So we have Oy and we have alpha. So let me keep highlighted the unknowns that we have. So we still need another equation, but we have the equation of the momentum. So we have the sum of the momentums at O equation, and so that's so the momentum that we have of 60 newtons. So this is minus 60 newtons because it's negative because it's going towards the paper, towards the screen, and minus the momentum of the weight, so it's also in the direction of the screen. So that's W multiplied by R, which is 1.5. And this is equal to the right hand side. So in the right hand side, we have this momentum. Okay, this acceleration is not producing momentum because it passes through this point, but this acceleration is producing momentum, and this Ig alpha term. So we have the Ig multiplied by alpha plus the momentum of the tangential force. So the momentum of the tangential force is the mass multiplied by the acceleration of g in the tangential direction, and multiplied by the distance, which is r. This rg to be precise. So this is rg. And so we can replace for the value of the tangential acceleration. So this is equal to Ig multiplied by alpha, which is unknown, plus the mass, and Ag is the acceleration, tangential acceleration, which is equal to alpha times Rg and multiplied by Rg. So we can solve here we can factorize alpha. So this is equal to Ig plus the mass multiplied by Rg squared multiplied by alpha. And in the left hand side we have minus 60 multiplied by the weight, which is 20 multiplied by 9.1 multiplied by 1.5, and this is our right hand side. So Ig is the moment of inertia of a bar, and so if we go to the tables, so this Ig is the mass multiplied by L squared divided by 2. Now Rg is also L over 2. So this is L is the total distance. So Rg is L over 2 as well. Sorry, and the first one is not over 2, it's 12. And this is mass multiplied by L over 2, but a square. So I'm going to leave it like Rg squared. So we have over 2 equations. So this is, the first equation is this one. The second equation is this one. And the two unknowns that we have are O alpha And in the second equation, we have alpha. We can actually solve for alpha from this equation. So if we solve for alpha, we get that alpha is equal to 5.9 radians per second. I will recommend you to do the math, to put it in the calculator. So now we take this value and replace it in this equation and solve for OY, the component of the force in the support, and we can solve for OY, and this is equal to 19 newtons. So with that, we solve all the unknowns of the problem. So summarizing, so we just have to set up the equations of motion for the normal direction, tangential direction, and the sum of the moments. So we have three equations, and in this particular problem, we have three unknowns, OX, OY, and alpha, and so we were able to find the components. Now we have a square cap question, which is not going to be a square question, but I want you to think about this. So we have a rigid bar that is released from the rest, so it's released from this point, from this position. And so the question is, what is the magnitude of the angular acceleration, and when is this maximum? So what angle the acceleration will be maximum? So 0, 90, 180, or 0 and 180. To give you a hint about the solution, let's set up the equation of moment. So we have a point over here, which is the point G, the center of mass, and so the weight is in this direction. So let me draw some axes here, so that G is supposed to be in this same direction. Okay, so now we have theta angle, which is in between these two. So theta we also will be in between these two, and if we draw perpendicular to the bar, so this section over here is 90 minus theta. The same thing is, this is 90 minus theta, so this is theta again. So this is theta, the angle theta. So now we can, so that's the only force that we have, the weight. So that force can be decomposed into two forces. So if we take the sum of the moments with respect to point A, that in terms of the moments, we have that the only moment, that the moment is only this component of the weight. So this is the weight, right? So is minus W, because is in this direction, so is towards the paper. So it's minus W multiplied by the cosine of theta, because is this component of the vector W, and multiplied by this length, which is L over 2. So that's the length. And that should be equal to the kinetic component, so which is the moment of inertia with respect to G plus the mass multiplied by R, G squared multiplied by alpha. And where did I take this one? From the previous problem. See, So this is the moment of inertia that we have from the right hand side, which is after doing the simplification, because this problem was exactly the same thing. So that was something rotating. The only difference is we have a moment applied. In this case, we don't have any moment applied here, it's just the weight. So we have alpha, and the question is where alpha is largest. So just look at the equation and analyze what will be the answer. I will post the answer somewhere else, or you can ask me the answer. Okay, let's continue with one second example. So in this example, we have a bar, and the bar is pivot at this point O, which is at a distance of 0.3 meters from one of the sides and 0.6 meters from the other side. Now, this is originally maintained in a horizontal position by a rope, but eventually the rope is cut. And the question is find the reactions at the pin O and the angular acceleration of the rod just after the cord is cut. So that means they are still in a horizontal position. So how do we proceed to solve this problem? So what is the plan? So let's get, what do we have to do first? The free body diagram and the kinetic diagram. So next, we have to set up the equations of motion. So how many equations of motion we have? 3, right? We have some of the forces in the tangential direction, some of the forces in the normal direction, plus the sum of the moments. And C, we solve the unknowns. And finally, what are the conditions that we have? So the conditions that we have is that omega, so initially it's not rotating, right? So omega is 0 at initial position. Okay, let's proceed. So first of all, our free body diagram and kinetic diagram. So let me draw, and let's duplicate this one. So we have the two. So free body diagram equal to the kinetic diagram. So let's say that this is the point O. So this is point O. And then we have on the left hand side in the free body diagram, we have the reactions. So the reactions are located at this point. So this is point O. So we have the reactions. Let me draw the reactions with a different color. So we have a normal, well, a vertical and a horizontal one. And what else do we have? So we call this OX and this OY. Any other force do we have in this side? We have the weight. So let me put this, which is the G point, and the weight, which should be downwards. And we don't have any other force because this was cut, so there is no force at that moment. So what are the kinetic components? So well, we have the acceleration. The acceleration, sorry, where do we draw them? in O or in G. So we have to draw them in G. So we have, let me put this so I can put this on the right hand side. So we have, this is a normal or tangential. So this is the normal component because it's towards the center of rotation, and we have, and this is moving downwards, so it should be, this should be the tangential and this should be the normal acceleration, and this is rotating in this direction, so we have Ig multiplied by alpha. Okay, so let's write the equations of motion. So equations of motion, we have that the sum of the forces in the normal direction, so we have in the normal direction, we have mass, sorry, what are the forces? So we have OX, and these are the forces, and equal to the right hand side, which is mass multiplied by AN, and AN is equal to mass multiplied by Rg omega squared. So our first, and what is omega at the initial point? 0, right? So what we have is, from this equation, we have that OX equal to 0. Now, the sum of the forces in the tangential direction. So in the tangential direction, we have the weight, the vertical support only. So we have OY positive minus W, and that should be equal to the mass multiplied by the tangential acceleration. So how is defined the tangential acceleration? It's R multiplied by alpha. So this is mass multiplied by R, and this is Rg multiplied by alpha. So if we rewrite this, so we have OY minus W equal to mRg alpha. From here, we have two unknowns, right? The two unknowns are OY, which is the same in the tangential direction, and alpha. Okay, so we have two unknowns because the first one is solved. So we need another equation. So the equation of the moments. So we have the sum of the moments at O. So that's so what moments do we have? So on the left hand side, so we have the moment produced by the weight. So we have the weight multiplied by Rg, because that's the distance. Let me put it this. This is Rg. And is equal to the right hand side, which are the kinetic component. So is the moment of inertia with respect to G multiplied by alpha, so this is the one, plus the moment caused by the accelerations, so plus, so we have two moments, so I should have been written this AT like mass multiplied by AT, and the upper one is mass multiplied by the normal acceleration. So we need to take the moment of this component with respect to O, because the moment of this one is 0. So the moment of this one is mass, let me write it in blue, mass multiplied by the acceleration of t, and times the distance. So the distance in between these two is rg. So the distance is rg, but the acceleration, the tangential acceleration, is rg multiplied by alpha. So this is ig, the moment of inertia with respect to the center of mass multiplied by the angular acceleration plus mass multiplied by the tangential acceleration, which is alpha multiplied by rg, and multiplied by the second rg is rg squared. So we can put this in numbers. So we have omega, well, let's put it in numbers. Well, let's expand a little bit this before. Omega multiplied by rg equal to the moment of inertia with respect to g. The moment of inertia of this rod is, according to the tables, is ml squared divided by 12 multiplied by alpha, but I'm going to factorize alpha because I have alpha at two sides, plus the mass multiplied by rg squared, and this multiplied by alpha. So in numbers, we have omega, the weight, and the weight is the mass, which is 15 multiplied by 9.81 multiplied by rg. So rg is this distance from the O to the center of mass, and so the distance to the center of mass is the center of this is 0.6, but 0 plus 0.3, so that's 0.9. Half of it is 0.45, and if this is 0.3, so this should be 0.15. Okay, so this multiplied by 0.15, so which is equal to the mass, which is 15 multiplied by L, the total length, which is 0.9 squared divided by 12, plus the mass, which is 15 multiplied by Rg, which is 0.15 squared multiplied by alpha. So with this, we have our second equation. So we have this first equation over here. This is our second equation. And so we have two equations, two unknowns. The unknown here is alpha. Anything else is known. So we can solve for alpha and then replace alpha in equation 1. And I'll let you do that. I'll give you the values. So from this one, we have that alpha should be equal to 16.34, and then by replacing in equation, replacing in 1, we'll have that the y component of the support is equal to 110.235 newtons. And so that's the answer. And with this, I'm concluding this lecture. Thank you very much.